Good morning everyone, I am Mr. Ish. You're joining me for this integrating by parts video, an interesting integration technique. Some of you might know this and some of you may not. It's a technique which has a formula that looks something like this. Integral of u dv is equal to uv minus integral of v du. There's a lot going on in this formula. It seems overwhelming at first, but like everything else it isn't once you become familiar with it. Integrating by parts technique is useful for those types of functions where you have a product of two functions which are dissimilar and they're not related to one another by means of a derivative or a function derivative relationship, for which then you would do polynomial substitution technique. Remember, when you have something which looks like this, a product of two functions, one of which is a original function and the other one is a derivative of that, you use a polynomial substitution technique. But when you have the product of two dissimilar functions, you don't want to use that, you want to use this technique. And you can also use this for those single function integrands where this is an interesting type of a function for which you want to do derivation of its antiderivative. Examples like would be doing something like this, like how is the antiderivative of this defined or determined, how are the antiderivatives of inverse trigonometric functions determined. Like these are excellent examples for this type of technique. These single functions which have very interesting antiderivatives, you can determine them by this. What we'll do in this video is just quickly show you how we derive this formula, and then we can show you some quick examples and some quick derivations as well. So this formula for the integrating by parts is not difficult to derive. You have to understand the fundamental theorem of calculus where integration and derivation or derivatives are opposite sides of the same coin. The chain rule of derivatives has a counterpart in integration, and that's a polynomial substitution technique. The product rule of derivatives has the counterpart in integration, and that's this integrating by parts. So everything here with the determination of this formula, it derives from the derivative of a function which is a product of two functions and from the product rule. If you take the integral of this derivative which has been derived from the product rule, it leads you to the formula for integrating by parts, and you can do that derivative over here and set it up as an integral, and I'm going to set these up separately across the positive sign into their own individual integrands. Here we're doing nothing more than the properties of integrals, where I've separated this, what I would have included as an integration scheme, into their separate integrals by means of the positive sign, and all of this is equal to this product of two functions. Here what you have to do is actually solve for this and take this on the other side of the equal sign. So let's do that. Is equal to, you have f of x gx minus this which came from the other side, g of x f of x dx. Now we know the formula for integrating by parts, as I showed you earlier, was this integral of u dv is equal to uv minus integral v du. How do we create this from this? It's not hard. You have to think of some substitutions. The substitution is this: if u is equal to f of x function, du is equal to the derivative of this dx. If v is equal to the g of x function, then dv is equal to the derivative of g of x dx. Now wherever you see these letters or these items, you put these letters over here. I have over here fx gx. F I know is a u, g of x is a v, then I have this minus sign, then I have an integral sign, I have g of x. G of x I know to be a v, f of x, derivative of f of x dx happens to be du. Then I have the equal sign, then I have this integral sign here. I have an f of x which I know to be the u function, and then the derivative of gx dx happens to be dv. And hence you end up deriving the formula for integrating by parts by taking the integral of the derivative which has been determined or derived from the product rule of derivatives. We'll start our first example with this product of two functions which are not related in terms of function and derivative, for which you would do the polynomial substitution technique. You have x and sine x, and it's an ideal sample for an integrating by parts technique. What you do in this technique is you have to do three substitutions or three determinations, which will then guide you through the rest of the procedure. The first thing you always have to determine is u. The next thing you always determine is du, which is the derivative of your u, and then you have to determine the v, because we know the formula to be this, and I'm only putting part of the formula, the main part, uv minus integral v du. This right here is the main part of the formula, and we know this equals integral of u dv. The question right here is your integral u dv. This right here is mirroring this right over here, but we have to do this part And we do that part by making these three substitutions. The substitutions should be smart, such that after the substitution, your original integrand becomes easier, not harder. And the best thing to do substitute here is x. And then the derivative of x is just dx, because it's 1 dx. And v then represents that integral of what remains, the integral of what remains. Once you've taken the x out by means of these two substitutions, the only thing that remains as the integrand is sine x dx. And you know integral of sine x dx is a minus cosine x. So now we have our u, du, and v. You have to plug them here in this formula, and let's do it. We have a uv. U is an x, v is this minus cosine x, the calculation of this v integral, minus cosine x, then you have a minus sign, then you have an integral sign v minus cosine x, and then du was just dx. See, we made a good smart substitution. Du was simply just a dx, and we have a very easy integral. If you didn't do a good substitution, you would really have to take this down another set of substitutions through another sequence of this integrating by parts technique. And sometimes you do, and sometimes you don't. Here, let's solve this out algebraically. We have minus x cosine x. These minuses cancel out. You have just a cosine x dx. This is easy. You have a minus x cosine x plus sine x plus c, and this right here is our answer for this integral question here, solved by integrating by parts technique, utilizing a substitution for u, from which du naturally comes out, and then the substitution for v. Let's look at this question. This question will be slightly more, tad bit harder than the previous one, but it's not overwhelmingly difficult. We have two functions here, products, and they're different, and you have to use integrating by parts technique. The first thing you always have to be thinking are these substitutions u, du, and v. Sometimes one round of substitution will solve your problem. Sometimes you have to do 2 or 3 rounds depending on the complexity of this integrand. The first thing we want to do is an initial substitution for u, and I'll go for x squared. Then I know du, the derivative of this x squared is 2x dx. The integral for what v will represent is that which remains. I've plucked the x squared out, so the only thing which remains is e to the x dx, and therefore it's just e to the x. Then I have to put everything here in this formula, uv minus v du, which all equals this right here, which is my integral u dv. But we focus here on this part of the formula, and we put these substitutions in. U was x squared, v is in ex, minus integral v is in ex, du is a 2x dx. Now look, we started here with an x squared ex, now we have an 2x ex. Order doesn't matter here, it's still one step away from completion, and we still have to do another round of integrating by parts, because I still have a product of two dissimilar functions which are not related and which cannot be solved by means of polynomial substitution technique. So I have to do another new round of substitutions. Here my next round will still again be u, du, and v. My u, I'll just keep it as 2x. I could technically have pushed this 2 out over here as a coefficient. I could have, but I won't. Du is a derivative of this, which is just a 2 dx. V is just the integral of what remains, is just an integral of e to the x, because I took the 2x out as a u substitution, and this is just ex. Now I do another round of this uv minus v du, but I have to be smart over here, and I'll continue it from this point onwards, because this point has been used up. And everything else prior to this you'll write as you see it. You'll have x squared e to the x, you have this minus, and then I'm going to create a parentheses because now I have to do another round of this uv minus v du. Here I'll have a 2x, my u, v is an ex, minus integral v is just an ex, and du here is a 2 dx. You see, we've lost a variable here, and we're good. And you can close this parentheses. So from this step over here, let's open up the parentheses. We'll have x squared e to the x, and we can bring this coefficient 2 right out. We'll have a minus 2x e to the x. This minus will impact with this minus to get a plus 2 e to the x, because the integral e to the x has a very easy antiderivative. It's e to the x plus c. You can isolate e to the x from all of this, and you can present a better answer, x squared minus 2x plus 2 plus c, and this right here is a good answer. And remember, in this question, it was slightly more complex, and you have to do 2 rounds of integrating by parts substitutions, and you always start with the u, and then you determine the du, and then you do v. And then for the next round, you have to make sure that you're continuing it from the proper point onwards, and you affect everything with any of the signs and the items that exist before it. So here's our next question, e to the x sine x slightly more difficult than the one we just saw. And you know everything starts here with good substitutions. Here I'll do substitution here for sine x because these are product of two functions which are dissimilar. You can't use a polynomial substitution technique, you have to do integrating by parts. du is equal to the derivative of this, which is cosine x dx. V is the integral of that which remains, e to the x dx, which is just e to the x. Put everything here in this formula, uv minus integral v du, because all of this represents your integral u dv. U is a sine x, v is an e to the x, minus, we have e to the x, du here is a cosine x dx. And you know we still have a product of two dissimilar functions. We have to do another round of substitutions. We have a u, du, and a v to be determined. U here will be cosine x. Derivative of this is a minus sine x dx. V will be the integral antiderivative of what remains, which is just e to the x dx, and that's e to the x. And from this point onward, you'll put these next round of substitutions, writing everything else before as you see it. Minus, and then put a parentheses here, because this integral sign gets replaced by this next round of substitutions. uv minus v du. U here is a cosine x, v is an e to the x, you have a minus v du, e to the x, du is a minus sine x dx, and you can close the parentheses here. I'm kind of running here into this other writing, but that's fine. In the next round, we'll open up everything. We have e to the x sine x minus e to the x cosine x. You have this minus and this minus becoming a positive. When that opens up with this minus, you end up bringing back the minus. E to the x sine x dx. Now this is a little bit of a conundrum which shows up, but it's easy once you recognize it. Our original question is this, and this is what we've gone so far, and it doesn't seem like we've gone anywhere, but we have, because all of this originally equals to our original integral, which was e to the x sine x, which was, you know, u dv. So you're seeing a minus over here, you're seeing a similar item here as this. You can take all of this on the other side and do a little trick over here. You have e to the x sine x minus e to the x cosine x is equal to, take this on the other side, it adds with the other stuff, e to the x sine x, because we're at the end of the day determining the antiderivative of this. Now all you have to do is just solve for this by taking 2 on the other side, and it divides. Our final answer will be e to the x sine x minus e to the x cosine x over 2 plus c. If you want to be presenting a better answer, you can isolate the e to the x and just do sine x minus cosine x over 2 plus c, and that would be your good answer. The only little trick over here, in addition to the fact that you had to do 2 rounds of substitutions, was this little hiccup that showed up. And you deal with something like this by taking this on the other side, combining it with your original integral, and then solving for the original integral algebraically by taking any coefficients which arise onto the other side, and that gives you your final answer. Now in the remaining of this video, we will just look at some of these derivation of antiderivatives for these unusual functions, which you know this is x ln x minus x, the antiderivative of that. You can use integrating by parts techniques to determine some of these useful derivations. If you have this integral of natural log x, how can you use integrating by parts technique? You start again with these items that you have to create in terms of substitution. Since there's only one function here, u must be equal to ln x. The only thing which remains, the derivative of this is 1 over x dx. V is the integral of that which remains. Since you've plucked the ln x out for u, the only thing which remains is this hidden antiderivative and dx, which is, going to give you the x. Now you put everything in this format, uv minus integral v du, which is equal to integral of u dv. This right here is my u dv. U is ln x, v here happens to be x, minus v is an x, du is just 1 over x dx. These things can cancel out. You're basically looking at x ln x minus integral of dx, which is easy, hidden antiderivative, which is just an x. You have an x ln x minus x plus c, and this right here is that unique antiderivative for something which looks like this, and you use integrating by parts technique to show you this. The inverse trigonometric functions have interesting antiderivatives. These are still single functions, and you can use integrating by parts technique to determine their antiderivatives. And let's do it. Start again with your u and then you have a du and a v to be determined. Similar to like the preceding one, you have a single function, u must be exactly this arctan. The derivative of this, you know, is 1 over 1 plus x squared. If you think back to your reference sheet, we have all of these available on our reference sheet. V is the integral of that which remains, which is nothing other than this integral dx, which gives you that x, the hidden antiderivative. You have the formula uv minus integral v du is equal to integral of u dv. This right here is my u dv. We have to put everything here in this part, and let's do it. We have a u, which is arctan or inverse tan. We have a v, which happens to be this x right here, minus v, which is an x, and du is this 1 over 1 plus x squared dx. Now when you look over here, you can do polynomial substitution technique, because very well designed for this type of stuff, and you can use it and you should use it. And if a is equal to 1 plus x squared, then dA, derivative of a, is equal to 2x dx, and dx is equal to dA over 2x. So this type of question will require you to employ integrating by parts technique along with polynomial substitution technique to take it to completion. And let's take it to completion. X tan minus 1x, or inverse tan, minus, we're doing the polynomial substitution technique. The integrating by parts technique is over. Now we have to finish it with this. We have an x sitting here. We have 1 over a, which was our polynomial substitution kicking here, and dA over 2x. I'm going to erase this over 2, and I'm bringing it out here as a 1 over 2. This x cancels out with this. So we have x inverse tan x minus 1 over 2 dA over a. You know we have a natural log which will come into play because we have a to the minus 1. An integral of a to the minus 1 has to be done. From here, we can take it to completion. We have x inverse tan x minus 1 over 2. The integral of 1 over a is a natural log a. So we'll do a natural log of a, but a was what? 1 plus x squared plus c, and this right here is the antiderivative of inverse tan. Inverse trigonometric tangent integral has this antiderivative. We'll end this video with this last derivation of an antiderivative for an integral involving an inverse trigonometric function, your arc cosine x, and it will be done again using integrating by parts but completing with polynomial substitution. U is equal to cosine minus 1, or inverse cosine x. Du is equal to minus 1 over square root of 1 minus x squared. Remember, this right here is the derivative of inverse cosine is this. V is equal to the integral of that which remains, which is just a dx, and here it'll just be integral of dx, which is x. You put everything into this formula, uv minus integral v du, which you should become very well familiar with. Here's my u, here's my v, here's my du. U is a cosine minus 1x. You can say uv or vu, it doesn't matter, order doesn't matter, minus v, which is x, and du is minus 1 over square root of 1 minus x squared. We shouldn't forget this dx over here, and dx. This minus can cancel with this and make it into a positive. Here you can very well handle this with polynomial substitution. A is equal to 1 minus x squared, dA is equal to minus 2x dx, and dx is equal to minus dA over 2x. Bring it in. X arc cosine x plus, you have x over, all of this is root a, and then minus dA over 2x. We'll make some changes right over here. We have a minus because all of this is multiplying with this. This minus is going to affect this and make it into a minus. The minus will make that positive into a minus. I'm going to bring this 1 over 2 out, and I can cancel this with that because I've already utilized it 2 over here. Clean this part out over here. The x's are cancelled. So what we have here is x inverse cosine x minus 1 over 2 integral of dA. These x's are already removed, or a to the 1 over 2. You can bring this up and do its integration. What you have over here, you'll have x inverse cosine x minus 1 over 2, and you're looking at the integral of a to the minus 1 over 2 dA. You have to do n plus 1 over n plus 1 for this polynomial or monomial over here. It's not hard. You get x cosine minus 1 x minus 1 over 2. You'll have a to the 1 over 2 or 1 over 2 plus c. This minus 1 over 2 plus 1 divided by minus 1 over 2 plus 1, that'll give you that. This 1 over 2 and this 1 over 2 will cancel out because this flips and becomes 2 over 1. Multiplies with 1 over 2 and they cancel out. as your final answer and resubstituting back for that a, which we know to be this 1 minus x squared, our answer is 1 minus x squared in the root plus c, and this right here is the antiderivative of an inverse cosine integral. And that's it for this video. That's all I wanted to show you in this integrating by parts, and we can always look at more practice questions in another video when we look at integrating by parts technique again. Remember again, the formula is this: integral of u dv is equal to uv minus integral of v du. All your substitutions are to be played into this part because this is the part you're actually solving for. Thank you for watching. Have a nice day.